can see mechanical energy into electrical energy. So basically, what is the possible application of this nanogenerator device? So before we coming to our result portion, so we can see here what are the possible applications. You can see like it can be used as a biosensor, human body energy harvesting, like tissue regeneration, cell stimulation, implantable devices, and many more like prosthetic, artificial skin, okay, like chemisensor, all these things. There is large number of applications are there. And that can be used, that can be solved by nanogenerator, and which is also self-charging. This is one more important part. It is a self-charging device. So we can self-charge that device, and we can convert that mechanical energy into electrical energy. Okay. So basically, how it works? So basically, its principle is based on the piezoelectricity that everyone knows. Okay. So I am not going to this part. So what is piezoelectricity? Everyone knows. Okay, when we apply some mechanical force to any material, then it converts its mechanical force into electricity. Okay, that phenomena we can say it is piezoelectricity, and that material which shows that property piezoelectricity, we can say this is the piezoelectric material. So here I have highlighted one material, that is PVDF. That I think many of you know. Like PVDF is polyvinyl lithium fluoride. Okay, so that PVDF shows the maximum ferroelectric property as compared to the other non-polymers. Okay, that is why we have focused on this PVDF. And but more importantly, PVDF has 5 polar phases. Now, what do you mean by that polar phase? So now you just see here is alpha phase, the orientation is different, or beta phase is orientation is different. So how can we achieve the maximum ferroelectric property? So if it shows like beta phase, like all the trans conformation or the Gauss conformation. So due to which net dipole will be maximum in this conformation. Okay, this is like expected model. Okay, so that is why we have chosen this polymer, and as well as this polymer has lots of advantage, like it is flexible, lightweight, cost effective, and high physiological coefficient as compared to other polymers, not ceramic. Okay, so this is some of the literature. Okay, you can see people are using PVDF, and they have used this type kind of material, perovskite material, and these two are my okay, so these two are my previous work, which has been published in Chemical Engineering Journal this year also, and this work I will discuss that published in that APL. So here motivation. So I am not going to this one. So how can we increase the efficiency of nanogenerator? That is one important task. So as we know, it is made up of some polymer. So it has lots of internal impedance. So our focus is to decrease, if anyhow if we can decrease the internal impedance of our device, then we can increase its output efficiency. So basically, how can we do? So we can include a conducting filler. Like in our previous work, you can see conducting filler, like I have incorporated that is multi-wall carbon nanotube, and that was PPY. PPY is polypyrrole, that is conducting polymer I have used. Okay, so here what happens? So as everyone know, like metallic nanoparticle also show some conducting polymer, it is metal. As we know, it is metal. So we have incorporated, there is manganese aluminum alloy. So why manganese aluminum alloy? Why not manganese metal or aluminum metal? It has also, everyone know, like if we use the only metallic nanoparticle like manganese or aluminum, it has ductility issue, then some corrosion issue will be there. But if we can make the alloy, so we can increase its efficiency, and it can be used for that is real life application for long term. Like it has less corrosional issue as compared to the pure metal. Okay, so now this is one. Before going to the result part, I will explain some. I will just let you know the basic of electrospinning technique. So basically, this is the electrospinning technique where we prepared the nanofiber mat or nanofiber rod-like structure or network-like structure. So this is the setup. This is our setup where if we put some electrostatic force, and due to which due to the electrostatic force of attraction, that fiber will prepare and it will deposit in the collector. Okay, so how it will look like? So basically, you can see here, this is the fiber structure. You can see this one. This is the fibrous structure. And this is our nanoparticle that we have prepared using arc melting method. And this is the data how we have increased the beta phase. So from FTIR analysis, like we have calculated F beta fraction from Beer-Lambert's law, and it is found that nearly that this 7.5 F means fiber. That fiber we have used, it shows maximum beta fraction, that is nearly 92%, and which is good for practical application. Okay, so this is our TEM data of TEM micrograph of our manganese aluminum nanofiber, and this is our very low cost device. You can see only use aluminum foil, and our device that is simple copper wire, and we have laminated this device. Just simple, like we have everyone knows our documents we always laminate to keep it safe. So I make my device safe by using this lamination film. Okay, and moreover, one important thing is you can see this is film. Like we have prepared using the drop casting method, and this is our nanofiber mat that prepared using electrospinning method, and we have compared these two results. And here you can say here I have not mentioned the beta fraction, but beta fraction shows for this one 79%, but for this nanofiber mat it is nearly 92%. Okay, so this is our result. That is now, as we know, dielectric property is also an important parameter for the nanogenerator application. Like our output voltage in oil also depends on the dielectric properties. So here you can see, like this is the dielectric property. So there is variation from low frequency like 10 to the power 2 to 10 to the power 6 hertz, and it shows 27. So actually dielectric constant of PVDF is only 8. But you have incorporated manganese aluminum alone, and due to the interfacial polarization, the beta phase is enhanced, and due to that enhancement of beta phase, our dielectric constant got enhanced. Okay, so for this one is also and dielectric loss is little more, but that is under that one around one. Okay, so this is a conductivity also, and this is one more parameter. This is the ferroelectric. Like yesterday some talk was there, like how this ferroelectric property is important for our device, like energy storage and energy harvesting devices. So that previous day Saket Asthana sir, Professor Saket Asthana has explained, if we can remove decrease this PR value, like remnant polarization value, so our energy storage density will increase. Okay, so because it is like integration EDP from PR to Pmax. Okay, so this area is for recoverable energy density. So from there also we can explain our energy storage efficiency of our devices. And so this is basically the result of our nanogenerator device. Okay, so here you can see this is the output voltage. Okay, so when we apply some pressure, that is nearly 45 kilopascal, and we got we've seen that this device that is prepared by nanofiber mat shows the maximum output performance, and which validates that is validated by our dielectric constant and ferroelectric property as well. Okay, so here and then also. And second thing is this voltage is coming from our device or not? How can we check that? So we have changed its polarity. Okay, and we have also seen this is the result, like forward bias and reverse bias. Okay, so if this with changing the polarity, if its result is coming like this forward and reverse bias, then we can say this output voltage is coming from our device. And second thing is, like with pressure also we have seen. So you can see from 13 kilopascal to 68 kilopascal we have varied with that pressure, applied pressure, and we can see that this after like this 55 to 68 kilopascal it is nearly constant, but before that it increased with the increasing pressure. And then this is also with increasing frequency we have also checked the device output performance. We can see that with increasing the frequency the device output performance also increase, but after certain limit it becomes stagnant. Okay, so and next thing is for any device more important is power, because without power we can't charge it for any for charging any portable electronic devices. Power is needed. Okay, so we have also calculated power. So before calculating power, we have calculated voltage and current with some load resistance. And we have seen we have a very low resistance from 0 to 25 megawatt. And we can see from there by Ohm's law. Okay, power is equal to from V square by R or I square R. So from there we have calculated the power. That is we got like at 5 megaohm power is maximum. And that is also from here you can see. So this is like this intersection. Sorry. So this intersection, that means this according to maximum power density theory. So that where the this portion is matching. So that merely that part will get the maximum power. Okay. So and after that we have used that our device in our shoe. Okay. So, and here you can see jogging, like jogging. So we can see some voltage spark is there. So when we got rest, so there is no spark. So from there also we can make a pedometer sensor, like how many steps we have we can like count. Okay, so for each step there will be each spike. So from that spike we can count the step. Once we count the step, then we can make a pedometer sensor. And we are working on working on it. Okay, so this is some approach model that we have that is explained in our work. That is basically, if you consider this is a nanofiber mat. So how can this interaction can take place? This is one big question. Yes. Okay. So I am not going to this part in detail. And this is some of the practical demonstration we have done in our lab. So I have to share with you this one. So basically here you can see, so we have lighted LED light using sieving machine, like Silai machine. Everyone knows this thing because it has some particular frequency. You can see, this one. So when you stop that machine, it will also get stopped. And for pedometer sensor also, this is our setup. So from there, from there we can find the output voltage when we are stepping on to our devices. And there also, like when tapping the devices, we are also getting some output voltage. And then like we can also make a breathing sensor. Like one of our work we have done this one. So breathing sensor means we can put it in our chest and we can monitor our breathing. Okay? And this work has been published in here recently, like 1 month ago. Okay? So thank you for your kind attention.
Hello, Tupan. Yes, sir. I have some questions. So it is it's kind of pedometer sensor with not a sensor. It is you have shown some power generation with this device that you have made. So how much is the power generation per unit area?
Yeah.
Because if you want to characterize properly, you have to mention the power generation per unit area, watt per centimeter square or millimeter square. More is the area, you expect more to be the output voltage, and hence you can drive more current through the load resistance which is connected across it. So this is one comment I have. Otherwise you could not compare from one device to other devices. So if you want to, let's say, market this device or make a product of this device, then every device should have very close properties. Now, talking about the properties, you are using some sort of carbon fillers like the multi-watt carbon nanotubes. So the mixture, or rather the composite that you are making with PVDF, So the number of, let's say, carbon nanotubes and the lengths of the various carbon nanotubes, they should be also as uniform as possible from the in the mixture that you have made. Otherwise, what happens that if you make 10 devices, then the 10 devices will have different power. All right. So, as for demonstration sake, it is very good demonstration as a pressure sensor, breather sensor, not just that, also power generation, because you are able to light the LED lamps with that. Right, and it can be also made very bigger if you make roll to roll. Like if you make more area, you will get even better. So you also mentioned that about impedance, right? So can you elaborate on what you mean by the impedance of the device?
Is it is the internal impedance of the device.
Uh,
Like it is like polymer, so it has some internal impedance. So if we can make some
I am not getting the internal impedance of a polymer. I can understand internal resistance of a cell.
Because this structure is like a cell person.
So impedance of a polymer is not clear to me, but internal resistance of a cell is clear to me. Do you mean that
Yeah,
internal resistance of a cell? Okay. So therefore, we need to therefore focus. You need to focus more on the how to decrease this internal resistance of the cell, because this is the culprit that is actually eating up the part of the power generated. So you may try to orient the polymer if possible. Orienting means to stretch it and then try to incorporate carbon fibers in it. Yeah. So if you do it that way, then it may lead to decrease of the internal resistance of the cell.
So maybe like the electrospinning technique is one of the technique we can use.
No, I am talking just spinning. It is orienting the chains of the polymer. So the chains the polymeric chains that in your device, they are all randomly oriented. They are not oriented in one particular direction. So this is actually the main cause of the impedance of the cell, because the charge carriers which move through this material, they experience not a easy flow from one electrode to the other electrode through the cell. So if you could orient the polymeric chains, then it would be possible to reduce the internal resistance of the cell. So that's my comment on that.
Sir, one more thing, sir. As you have said, sir, like power. So actually, this device is made 1 centimeter by 1 centimeter area, and we got something like power here. I think this is like 49 or 49 something microwatt per centimeter square.
Okay.
This is our power. We have calculated that.
So therefore the race is now on how to increase it further. Yeah?
That is where we are looking.
Yeah. Okay, all the best.
Okay, thank you.
In the figure J, what is the gap between 6 to 8 voltage?
Okay.
What is the reason behind it?
No, that I stopped the fitting on the device. Like this is like when I am stepping on the device. This is like this is the voltage. Okay, so I just stop. So this is like no output signal.
No questions there. Let us thank Mr. Sujit.
So we can also convert this clipping energy into electrical energy.
But more power, more.
Okay, more. I need more power from you. Okay, thank you.
So, we have more two speakers. I hope we can continue after 3 weeks. 3 weeks.